Let's look at an alternative notation for the average rate of change. And this notation, I think, will be more common when we get to the definition of the derivative. And again, it's just different notation for the same exact concept. So if I've got some interval from A to B, and let's say A is not equal to B. So when you look at this interval from A to B, it looks like a little line segment instead of a dot, right? So what I can do is I can let h be the distance, right? So we'll let h, right? H is the distance from A to B. So we'll say that h is just b minus a. So instead of writing b here, I can just write a plus h. So, I mean, what is b? It's start at a and move out a distance of h. So here I can write a plus h instead of b. So now, instead of looking at the interval from a to b, I'm now looking at the interval from a to a plus h. So the new notation then for the average rate of change of f on the interval from a to b is now just the average rate of change of f on the interval from a to a plus h. What is that? Well, it's f of a plus h minus f of a over the difference of the x's, so a plus h minus a. So here the a's cancel, and I'm just left with an h. So now, how do we want to use this? Well, remember when we are looking to compute instantaneous rates of change, what are we doing? We're taking this in, so if we want to find the instantaneous rate of change at the point A, so we'd start here at B, and then we would move the point B closer to A. So by moving B closer to A, I am really moving A plus H closer to A. How can I move A plus H closer to A? I can do that by moving H closer to 0. So we should note to move B equals A plus H towards A, right? To move A plus H towards A is the same thing as to move H closer to 0. Right? So again, to move B closer to A is the same thing as moving A plus H closer to A. So that's the same thing as moving H close to 0, right? When H is 0, A plus H is just A. So now we want to use this fact to compute an instantaneous rate of change, maybe with a little less computation, a little less numerical computation. Okay, so let's look at an example using this difference quotient. Remember, I don't think I defined that last time. The difference quotient is just the f of a plus h minus f of a over h. So right, the difference quotient is just the average rate of change of a function on the interval from a to a plus h. Anyway, so we want to find the difference quotient, or the average rate of change of the function x cubed on the interval from 1 to 1 plus h. So we'll draw a picture and see what that tells us in a second. And then we want to use part A to see if we can make a guess for the instantaneous rate of change at the point where x is equal to 1. Okay, so the first thing we want to do is to find the difference quotient of the function x cubed on the interval from 1 to 1 plus h. So again, that's just the average rate of change of the function x cubed on the interval from 1 to 1 plus h. So remember what that is. It's just the slope of the secant line connecting the 2 points 1 comma 1 cubed and 1 plus h comma 1 plus h cubed. So again, this is the point 1 comma 1, And then if this is any old x coordinate 1 plus h, then this thing is 1 plus h comma 1 plus h cubed. So I'm just taking 1 plus h, plugging it into the function. That tells me the height. So to find the difference quotient, again, it's f of 1 plus h minus f of 1 over h. So what's f of 1 plus h? Again, plug 1 plus h everywhere you see an x. So that's just 1 plus h quantity cubed minus everywhere I see an x, I'm going to plug in a 1. So minus 1 cubed. And then we want to divide that by h. So this would be a good final answer, but let's see if we can simplify this thing a little more in such a way that we can see what happens when h gets close to 0. So this is a secant line. How do we get a tangent line? We want to do that in part B, so let's go ahead and get what we need to get to set that up. So to get the tangent line, we want to take this point here and move it close to where we want the tangent line. So remember, we want the tangent line when x is equal to 1 in part B. So I'm going to take this endpoint and move it closer to 1. Because remember, the closer that the points get together, the closer we are to a tangent line, right? So if you've got 2 points, a secant line, 2 points that are really close together almost gives us a tangent line, and we're just using estimation at this point. So we'd like to make h equal to 0 in order to sort of eyeball it, right? It'd be great if we can plug 0 in for h, but we can't do that. So let's see if we can get rid of the h in the denominator here, right? So here I'm just going to FOIL 1 plus h cubed. So when I do, I can use the binomial theorem or FOIL it out however you want. So I get 1 plus 3h squared plus 3h plus h cubed. So that's what's in the parentheses here. Do not make the mistake of saying that 1 plus h cubed is 1 cubed plus h cubed. That is very false, right? Remember that you need to FOIL. So again, 1 plus 3h squared plus 3h plus h cubed. And then we want to subtract 1, and then we want to divide by h. So what's going to happen is that the 1's will cancel, and now once that happens, each one of these 3 remaining terms has an h in it, so I can factor an h out and then cancel the h's. So here I'm going to get, instead of 3h squared over h, I just get 3h. Instead of 3h over h, I just get 3. And instead of h cubed over h, I just get h squared. So this would be a good final answer, right? This is our average rate of change. This tells us the slope of the secant line where h is any old number, right? So now you've got a formula, another formula for the slope of the secant line. And this is true as long as h is not equal to 0. So the average rate of change is the same as this function of h as long as h is not equal to 0, right? Because that wouldn't make any sense. So now we can use this thing to see exactly what the instantaneous rate of change is. So how do I find that? I'm going to move 1 plus h close to 1. That's the same thing as moving h close to 0. And so you can see what happens when h gets close to 0 in this thing. This piece will get close to 0, and this piece will get close to 0. So when h gets close to 0, 3h plus 3 plus h squared, right, this thing will get closer and closer to 3. So we would guess that the slope of the tangent line is going to be 3. So here's a good answer for part A. Right, that's the slope of the secant line. This would be a good answer for part B. How do I get from part A to part B? Once I have canceled the troublesome factor in the denominator, once I've gotten rid of the h in the denominator, I can basically just plug 0 in for h, and so that tells me that the slope of the tangent line is 3.